Today in this presentation, just going to go through some concepts. So what is a diagnostic test? And we're going to talk about sensitivity and specificity. We're going to see plenty of 2x2 tables, and we're going to talk about the cutoffs, predictive values, and the influence that the prevalence has in predictive values. And then briefly the comparison of two test systems and multiple testing, so either sequential or parallel testing. So first with the basics. So what is a diagnostic test? What we typically think about a diagnostic test is a laboratory test procedure. So looking for liver enzymes or for an antibody. Really is any device or process designed to detect or quantify a sign, substance, tissue change, or body response in an animal. And those obviously can also be applied at a herd level of other method or level of aggregation. So a clinical examination, temperature measurement, and any kind of process that is going to help us in our decision-making process, which is going to have really two settings. We could use them in a clinical setting, so really to determine what are we going to do next, whether the animal has the disease or not, or yes, throughout our decision-making process, or in a research context. And it is the characteristics of a diagnostic test are key to assess what the data quality is going to be of our research when we apply them. So we need to understand them a little bit, and that's why I'm going to talk also a bit about inherent characteristics of the test. Obviously, we can have diagnostic tests that are going to be directly identifying the pathogen, like our culture, PCR, and virus isolation. So it is important that we understand their characteristics and things called the culture. We know that it's low, there's low sensitivity. With PCR, we know it's very high sensitivity and specificity, but also that sometimes when applied with certain, for example, RNA viruses, should that RNA virus mutate, then maybe our PCR might not be as specific anymore. So we need to understand this. The same with the indirect methods, so methods where we are trying to identify the. Also, we need to understand the biology of the disease that we are studying or researching. So we need to understand when are we going to be able to detect the pathogen and when that antibody response is going to kick in, and we're going to then be able to apply our indirect methods. So this is kind of basic information that we need to know very well, so that then we can apply our diagnostic test in the research as required. And of course, we can have screening tests, which are typically applied to asymptomatic animals or people, so animals that may not have the disease, and then it's either to guide us as to have a diagnostic test or to do things like a seroprevalence study. Diagnostic test then is going to determine whether the animal has the disease or not, to confirm or to classify the disease. And then just a couple of things, and this is just to touch briefly, is the analytical sensitivity. So this is in terms of a test and in terms of a certain matrix as well, a certain sample type. So this refers to the lowest concentration of either the chemical, the organism, or substance that the test can detect. So this is a measure of this is the limit of detection of an assay, which is the estimated amount of analyte in a specified matrix, specified sample type, that would produce a positive result at least a specified percent of the time. So these are concepts more to do just with the actual laboratory test. The analytical specificity then is the capacity of the test to react only to one chemical compound. And in fact, in some cases, in some PCRs, it's also necessary to make sure that it's not going to react with other genetic material present in the sample. And then a couple of concepts that if you work in diagnostics, you will be familiar with is the accuracy of your test, so the ability to give a true measure. And then also precision is just about how consistent results are, whether they are accurate or not. Because as you know, the repeatability is one of the characteristics of our test. But then let's move on now to the sensitivity and specificity, and I'm sure a lot of you are kind of familiar with these. So the sensitivity is the proportion of true positives that are correctly identified by the test, and the specificity is the proportion of true negatives that are correctly identified by the test. And they can be quoted well either as a probability between 0 to 1, or as a percentage. So how do we get to these sensitivity and specificity? Is because we compare our test, so our test outcome, with our gold standard. So, diagnostic tests are typically evaluated against this gold standard, which is a test that is absolutely accurate. So it diagnoses all the disease and misdiagnosis known. But this in real life is very, very hard to come by. Not only just due to the actual test characteristics, but also to biological variability. But this is how we do it. So we put our results, test the same population, and we put our results in a 4x4 table. So really what we're looking at is that the population that is positive to both the gold standard and our test outcome, those are going to be our true positives. Those are positive by the gold standard but negative by our test are going to be our false negatives. And that's a type 2 error in statistical hypothesis. In terms of those that are negative by the gold standard and negative by our test outcome are going to be our true negative population. And those that are negative by gold standard but positive by our test that we are evaluating are going to be our false positives. And these are type 1 error. Yes, in a statistical hypothesis. So let's look at it just with a little bit more detail. So sensitivity really is the proportion of those animals with the disease that are correctly identified by the test. So it's the likelihood of an individual having the disease delivers a positive test result. And we can calculate this with the following formula. So what we do is we calculate the number of sick animals, so our true positives, the A here, and we divide it by the number of all sick, so the true positives and the false negatives. So those are the ones that were positive by the gold standard, but our test determines that are negative. Specificity then is the proportion of true negatives. So those are individuals that do not have the disease that are correctly identified by the test, so that give a negative result in our test. Or we can also talk about this as the likelihood that an individual will give a negative test result without the disease. And the way we would calculate this is by dividing the number of healthy animals with the negative test results. So those are our true negatives. And we divide it by the false positives plus the true negatives. So those false positives are those ones that were determined negative by the gold standard, but positive by our test. So as a summary of these, we have our sensitivity here, where we have our true positives divided by all the ones that were true positives plus false negatives, and the specificity that we have the true negatives divided by the true negatives plus the false positive. And let's say that also something that I meant to say at the very start of this section is that they will always refer to a certain test and to a certain disease. So these are just specific to the disease and the test. And they are very much related to each other. So we're going to explore this a little bit more. We're going to explore how they relate within one population. And we're going to look at see if the sensitivity and specificity are constant in regard to a particular disease. So in here we have a population of fish. So the red ones are diseased and the green ones are healthy. And we want to separate the population of diseased and healthy. So if we get a tight mesh to get this fish, we're going to catch all the big fish, but we're also going to catch some of the small non-diseased fish. So we have a high yield, but it's not very accurate. So not all the results that we have in this mesh are what we're looking for. We can use a wider mesh, which means that we will catch none of the small fish, but we are going to lose some of the big fish, some of the ones that were actually diseased. So it will be accurate. So the animals that we get will definitely be diseased, but there's not going to be a big yield. So let's look at that with a bit more detail. So a tight mesh really equals to a high sensitivity. So we fish out many, if possible all with infection, but we're going to get some of these false positives. Some of the little ones are going to come through. So if an ELISA has this 99.5 sensitivity, it means that 995 out of 1,000 animals are really positive, and 5 out of 1,000 are false negatives. In terms of the specificity, the wide mesh means a high specificity. So those that we take out, they really should have the disease. The problem is that we let some escape. So we have an increase in false negatives. So if we have an ELISA with 99.5% specificity, it means that 995 out of 1,000 animals will be really negative, and the other 5 will be false positives. And we're still going to explore this a little bit more in terms of the cutoffs, because sensitivity and specificity, when we have these continuous variables results, they are really very much related. Sorry. So let's see if we have a test with a sensitivity of 98% and a specificity of 95%. And a prevalence of 10%. So if we have a 500 population and we have a prevalence of 10%, that means that we'll have 50 out of those 500 will be infected. With a sensitivity of 98%, it means that 98% of 50 will be detected, so that is 49. So then that means that one of those is going to give us a false negative, because it really is positive, but our test is not able to detect it. So again, that's the 2%. That's the 1 minus sensitivity. Yeah. So 98% of our 50 is our 49, and then the remaining is the 2%, which is 1, which is the false negative. And then what about the specificity? Well, our non-infected animals are 450. So 95% of those will be correctly identified. So I should have put that too there. But the remaining 5% will not be, will be false positive. So those are our 22 tests. Test positive. So let's explore what happens with the with our cutoff value. So typically, sensitivity and specificity, they can be calculated just for tests that have only a positive or a negative result, for example, the presence of a parasite. But we typically use them with variables that are measured continuously. So we have, for example, an ELISA result or even PCR results. So what we will have is that we will need to decide on a cutoff point, because there will always, we will have results on an ordinal scale, and we'll have to decide where do we put that cutoff point. So for these continuous test variables, when we decide this cutoff point, so this C line, there is a relationship, there is an inverse relationship between the sensitivity and specificity. So in the top graph here, what we see is the frequency distribution of a variable in a healthy population. So those are this is negative, and the lower is the frequency of distribution in a diseased population. So it might be a bit clearer if we move to this graph. So what we have is, here is the number of positives, and what we have is the healthy on the left-hand side, the diseased on the right-hand side, and obviously there is this overlap, and so what we have in the disease negatives is when after we have the cutoff point, those animals that are really disease positive and we're going to consider positive are going to be our false positives. And of the right-hand side, so in the disease positive ones, but the ones that are on the left of our cut-off point is going to be our false negatives. And I'll show you this with data, and it might be a bit easier to understand. So what we have here is on the table, on the left-hand side is the value of our test. And then we have the healthy population, and we can see their values in the middle column. We can see the ill population, and we can see their values. And as you can see, there is an overlap. So the population in green are the ones that are negative. And as you can see, when we go on the right-hand side of our cutoffs, these are going to be considered positive, but they are really negative. So they are our false positive. And the opposite happens also. So those ones that are positive, that are in red, once we have them on the left, our cutoff point, they're going to be considered negative, and therefore they will be our false negatives. So it is, as you can see, it is extremely important to be able to determine our cutoff point rightly, because there is always going to be some level of compromise. So if you put the cutoff to the right-hand side, you're going to have an increase in false negatives, and the opposite as well. So how do we choose our cutoff value? The cutoff value, it just, first of all, it depends on the purpose. So, for example, if we want to do an initial screening, we might want an increased sensitivity. And it also, yes, it's very important to know what the purpose of determining the cutoff value is. And there are several ways of calculating it. There is, in some cases, they can use the two 2 or 3 standard deviations greater than the mean of the test values of the healthy animals, or you can choose values that minimize the cost or misdiagnosis. And also there's the possibility of using likelihood ratios and also ROC curves. And the likelihood ratio just gives a good summary measure of a test performance, which is independent of prevalence, because anyway, we will see afterwards that the predictive values are actually very much dependent on our population, on the prevalence within our population. So the likelihood ratios, we can have a likelihood ratio of a positive test result or a negative test result. Of a positive test result is the ratio of the proportion of affected individuals that test positive, and the proportion of healthy individuals that test positive. So as you can see, is sensitivity divided into 1 minus specificity. How do we interpret this? So the higher it is the better. So for example, if we have a likelihood ratio of 110, means that a positive result is 110 times as likely to come from an animal with disease as from an animal without the disease. And the fact is that is this likelihood ratio of a positive result that we can use for determining the cutoff values. The likelihood ratio of a negative test result is the ratio of the proportion of affected individuals that test negative and healthy individuals that test negative. So as you can see, there is 1 minus the sensitivity divided into specificity. Now, the good news is that you don't need to memorize really all these of the formula. There are a lot of resources that can be used. I'll give you some afterwards, and with the details of your test, you can get all these calculated. And I'll show you a ROC curve a little bit further on. But before, let's continue with the cutoff and the actual effect that this is going to have. So let's say this is the same as we were looking before. So we have our healthy animals on the left of our cut point, and this is on the right, and those test positive and negative. So what happens if we move the cutoff to the right-hand side? Well, the sensitivity is going to come down, and the specificity will increase, and we'll have an increase in false positives. As you can see, if we move that cutoff to the right, it's just the area will increase. If we move the cutoff to the left-hand side, the sensitivity will increase and the specificity will decrease. So as you can see, they are very much related. And again, this only refers to a certain test, a certain disease. So another way to determine another characteristic of our test, important characteristic, is to look at the predictive values. The positive predictive value is the percentage of individuals who test positive who also have the disease, or the likelihood that an individual who tests positive will have the disease, or the likelihood that a positive test is really positive. And how do we calculate this? Well, we go back to our table where we're comparing our test outcome and the condition. And what we look is that we look at the number of sick people with a positive test result, so our true positives, and we divide it within all the animals with a positive test result. So with the false positive plus the true positive. The negative predictive value, which refers to a specific test and a specific disease, is the proportion of individuals who test negative who do not have the disease, or the likelihood that an individual who tests negative will not have the disease, or a probability that a negative result is really negative. So again, the way that we calculate is by looking at the healthy, so the true negatives, and we divide those with the true negatives plus the false negatives. So all the number with a negative test result. And now what we can see is that really this is the complete table. So we can see how to calculate sensitivity. We'll really concentrate in this first column. To calculate the specificity, we'll concentrate on the next column. And then the positive and the negative predictive values on the opposite direction. So you can see the relation between all of them. So what about prevalence, and what effect could that have in our predicted values? Well, first of all, Jordan has said this, so the prevalence is the proportion of individuals in a population who have the disease at a given point of time, or the probability that an individual chosen at random for the population has the disease. So we have in this table here, we have a population of 10,000 animals with a prevalence of 20% and a sensitivity of 98% and a specificity of 99%. And when we calculate our positive predictive value, we can see that is 0.96. What happens if we reduce the prevalence? Well, with the same characteristics of the test, the same population and same sensitivity and specificity, actually our positive predictive value now is going down to, 49.7% or 0.497. So as you can see, it's got quite an effect. So in this graph here, what we see in the x-axis is the prevalence of the disease, so from 100 to 0.1%. And on the y-axis, we see the predictive value of a positive result. And we have two tests. The one with the dots has got a 70% of sensitivity and 70% specificity. And the one with the crosses has 99% sensitivity and specificity. And what we can see is that at low prevalence, even a nearly perfect test is not great as having a good low a predictive value. So the number of false positives really would be unchanged after the disease was eradicated. And as you can see, as the prevalence increases, so does the predictive value of a positive test result. So really, what this shows us is that the acceptable levels of sensitivity and specificity are really going to depend on the stage of our disease eradication or control. And typically at the end of our campaign, we're going to be looking for a more sensitive or and a specific test. But as you can see, even with one that is close to perfect, we still have difficulties at the end. So for these, well, there can be other techniques applying, perhaps serial testing or other ways. So let's explore a little bit of the influence of the prevalence on the predictive value. I would like you to go to this WinEpi website and go to the diagnostic part and the estimation of predictive values. And with these details here, 10% prevalence, sensitivity of 99% and a specificity of 99%, and a population of 10 million, calculate the sensitivity and specificity, sorry, no, sensitivity, just fixated, a positive predictive value, the true positives and the false positives. And put your results in the chat. Let me see if I can put the address in the chat.
The address is already in the chat, Maria.
Perfect, thank you. Okay, can everybody find the website okay?
What do you want in the chat? The complete results or specific?
Yeah, you think yes. So that's at least I know when some people are getting the results, and then I can share mine. And also, yes, very good. And also look at the numbers of true positives and false positives, because it's going to be interesting to see. Okay, so you should have it on the same results as you have those. So we have a positive predicted value of nearly 92%, which is really good. And we have 990,000 true positives. It's quite a lot, but it's a population of 10 million. And 90,000 false positives. Okay, so let's have a look now. Exactly the same characteristics of our test and population, but now we're going to go to the end of our disease eradication, and we're going to have 0.01% of prevalence. Okay, so yeah, so as you can see, if I can move it, now our positive predictive value is 1%, and only 992 positives, but we have 99,990 false positives. So this is something to bear in mind. So what can we do to increase the positive predictive value? So in some cases, it can be used in a population with higher prevalence. So for example, in the UK, the brucellosis used to be so it used to be targeted in the animals with an abortion that will get several tests done at the same time. So that's one of the way, or we can target animals with a certain clinical presentation, for example. We can use a more specific test with the same of higher sensitivity. And as the specificity increases, so does the positive predictive values. And we can also use more than one test. And this is something we're going to explore in a couple of slides. But before just to summarize, and as you can see, about the limits of the diagnostic tests. So first of all, the quality of the diagnostic test is really going to determine if you can use it for a specific purpose or not. And this is why it's important to know all these data. So if you have a test with a specificity of 92%, you cannot use it to detect a threshold prevalence of 1%. And also you've seen that the sensitivity and the specificity can really be varied by changing the cutoff value. So it is very important to know how to determine this cutoff value. And finally, that the diagnostic test has to be chosen looking at the sensitivity and the specificity, and also very important is the prevalence, especially for our predictive values. And of course, there's going to be an influence of this imperfect test on sample size, and Jorn is going to explore that in the next session. But typically, the more imperfect our test is, the higher the sample size that we need. So basically a population can be free even if you have positive test results, as we've seen with the exercise earlier. So even if you have a good test but a very low prevalence, you might still have quite a large number of false positive results. So in this example, in detection of disease on a 5% threshold prevalence, 95% confidence, and a population size of 10,000, if we would have a complete, perfect test with 100% sensitivity and specificity, we would need only 59 samples. But with a not so perfect test, so you can see there the sensitivity and the specificity, we're going to need 376 samples, and that's including a cut point number of reactors, of 27 reactors. But as I said, Jorn is going to explore that on the next session. So I was saying we can compare the two testing systems. So really, so as you can see, to calculate the sensitivity and the specificity of our test, of the test that is we're evaluating, we require kind of an independent, valid criterion, and this is our gold standard. And this is what is going to define the true status. But as you probably know, and these is just, they're not always perfect. And sometimes we can even, there's a need to use more than one. The fact is that a reduction in the sensitivity of the gold standard is going to cause a decrease in the apparent specificity of the test that we are evaluating, and a lower specificity in the gold standard will cause a decrease in the sensitivity of the test evaluated. One point to make also, it's just the gold standard should be applied to animals, both health and disease, that are representative of the population. And in terms of comparison, like you've seen, like we can use the table to compare our evaluate our test with our gold standard. But also another way that we have to compare tests is by using a ROC curve. So these are receiver operating characteristic curves, and what we are doing with them is to plot the sensitivity and the false positive proportion with different cutoffs. So you can see there the different cutoffs and the actual sensitivity and the specificity that they will obtain. So the closer that our curve is to the left top corner, the better our test is going to be, because it's going to achieve, it's going to be closer to 100% sensitivity and specificity. When we compare two tests, what we would have is two curves one from each test. And what we will find is that we can calculate the area under the curve. So the higher the area under the curve, the best the testing system. Now, all these, again, as I was mentioning before, there are good resources online to be able to calculate these with your results. Yes, and I hopefully have a slide with some of those resources later. So let's get to the final part. As I was mentioning before, one way to improve our tests is also to use several tests either at the same time or one after the other. So these are our either parallel or sequential tests. So the parallel testing consists in conducting 2 or more tests at the same time. The animals will only consider to be affected if they are positive to any of the tests. So let's say we conduct 4 tests, the animal is positive to 1, that animal will be considered positive. So what effect does this have? Well, it increases the sensitivity and the negative predictive value, but reduces the specificity and the positive predictive value. So we're less likely to miss a disease, but the false positives are also more likely. So effectively, we're asking the animal to kind of prove that it's healthy. And this is, for example, applies to the same example I was saying earlier, but how the brucellosis testing used to be done in the UK in terms of an aborted animal. Then we'll have a battery of tests, culture, serological tests, sometimes tests on the milk. And if that animal was positive to one of them, that animal was considered positive. What about the sequential testing? Well, what it means is that we conduct 2 or more tests in sequence, so one after the other. So typically the animals are considered to be affected if they are positive to all tests. And what you would do is you would only do a second test if the first one is positive. So this approach increases the specificity and the positive predictive value. But in turn, as we've seen, there is also always this relationship reduces the sensitivity and the negative predictive value. So really, it does increase the risk that the disease will be missed. And really, the test with the highest specificity should be used first. This is to reduce the number of animals that you need to test again. So let's see these 2 approaches now compared. So again, in parallel, we test performs at the same, so the tests are performed at the same time and the results are then combined. In the sequential, the second test is only performed if the first one is positive. In the parallel approach, the animal will be positive if any of the results are positive. In the sequential, all the results will need to be positive. In the parallel, we obtain higher sensitivity and lower specificity, and the sequential higher specificity and lower sensitivity. So really, in the parallel, we rule out a disease, and the sequential will rule it in. The parallel is used a lot of the times in rapid assessment. So let's say if you have an animal that comes in the clinic, you need to know what happens, and several tests are done at the same time. And the sequential, it is used, for example, in disease eradication programs where you do test and removal. So you do a first test, and if the animal is positive, you might do a second test just to make sure that that animal is positive before removing the animal from the herd. So let's see really the effect that these are going to have. In here, and I've used the same WinEpi website that I've given you for the for the exercise earlier, so you can use that to test these things. So I put a test A where it has a sensitivity of 80% and a specificity of 90%, and test B with a sensitivity of 90% and a specificity of 99%, with a prevalence of 20% and a population size of 200,000. So what we see is that when we apply them serial, so one after the other, we see how the sensitivity reduces, but the specificity increases. And when we apply them in parallel, we have a higher sensitivity, but a lower specificity. And you can see also the effect that is had on the positive predictive value and the negative predictive value. So again, you can find those in WinEpi, and you can play around with those to get also an understanding. So one consideration with these is that the test must be independent. So they must be measuring different things. So for example, a PCR and an antibody testing, and this is because, our formula is based in that if they are correlated, so if they are, for example, two different antibody tests measuring the same, this has an effect on the way that you would calculate the sensitivities and the specificities. So the test must be independent. And then we really do need to have an understanding of both the test and the disease characteristics. For example, we know that UODs or paratuberculosis it doesn't normally manifest clinically in animals under 2 years old, and we're very likely not to find any antibodies or indeed any cultured pathogens. So also BSC testing in animals under 12 months old is it's probably a waste of time because we're not going to find any positives. So so it is important not only in parallel sequential testing, but obviously in the application of diagnostic testing in general. So in summary, we have the diagnostic test characteristics are going to influence very much the quality of the data obtained with our research. We can change the sensitivity and the specificity, changing the cutoff value, but it's going to have an inverse relation. So it's always going to be a relation between the two. The diagnostic test must be chosen by looking at not only sensitivity and specificity, but also the prevalence. As I mentioned, we need to know the disease and the test characteristics, and multiple tests may be used. But as mentioned, you have to really know the strategy and how you're going to apply it to have a sense of the effect that this will have on the actual sensitivities and specificities and predictive value.